Part 2 of Chapter 2b about the overview of electroanalysis. We are thinking about the reversible reactions, and I mean reversible Faraday reactions for cyclic voltammetry. Of course, we have reduction and also oxidation. Also, the kinetics of charge transfer for the reduction and oxidation is really fast. The overall kinetics of this system is totally determined by mass transfer kinetics, or shortly, the diffusion. As you know, the diffusion is induced by concentration gradients. Therefore, I can say concentration gradient determines the current for the reversible Faraday reactions. So I'd like to explain about the cyclic voltammograms in terms of or from the viewpoint of concentration gradient. Here is a big cyclic voltammogram, and y-axis is the current in microampere and x-axis is the potential from plus 0.8 to minus 0.2. So following the clockwise direction, I have swapped the potential from the positive value to negative value and then reverse the potential shift from the negative value into the positive value. I'll check the concentration gradient for several points like A, C, D, E, G for the cathodic process, and then I, J, K for the anodic process. This system is about ferricyanide electrochemistry. Fe3 plus in ferricyanide with some electron, one single electron, then finally goes to ferrocyanide having Fe2 plus. So actually this electrochemistry based on between Fe3 plus and Fe2 plus. Also, this electrochemistry is well known as the very reversible, that is to say very fast kinetics electrochemistry. So let me start with the point A here, and also please assume that we have only ferricyanide in electrolyte without without ferrocyanide in this case. So let me say 1 millimolarity of ferricyanide is available in this electrode without 0 millimolarity without ferrocyanide in this electrolyte. That is the starting point. We have the electrolyte. So at the point A, of course, we have 1 millimolarity of Fe3 plus and 0 molarity of Fe2 plus in electrolyte in the bulk and also on the surface of electrode. Then let's apply some negative potential into the electrode. Then we are going to B and C. At the very earlier potential sweep range, we don't have very tiny current. The tiny current is caused by a non-Faraday process for electric double layer formation. But before the point B, we don't have any Faraday current responsible for the reduction of Fe3 plus to Fe2 plus. However, around the point B, we have obtained the current responsible for the reduction process. Then let's go to the C point here. At the C point, some portion of Fe3 plus is converted or reduced to Fe2 plus. So on the surface of electrode, you have some the concentration gradient of Fe3 plus and also the concentration gradient of Fe2 plus. Right now, Fe3 plus is consumed. So in this case, at the surface of electrode, we have, for example, 0.5 millimolarity of Fe3 plus are there. So let me say this is the 0.5 millimolarity of Fe3 plus on the surface. Therefore, then also at the same time 0.5 millimolarity Fe2 plus is generated at the surface of electrode. Therefore, you can find some positive concentration gradient of Fe3 plus around the surface of electrode. At the same time, the negative concentration gradient of Fe2 plus is developed on the surface of electrode. This concentration gradient indicates the current. So at the point A, I mean at the time equal to 0, we don't have any current because there are no concentration gradient for the oxidized species or Fe3 plus. At the same time, there are no concentration gradient for the Fe2 plus. However, at the point C, here, we have the concentration gradient. So we could have obtained a value of the current. This concentration gradient of oxidized species, maybe following this one, the slope of this line is equivalent to a value of the current. Let me say that is the 14 microampere for the reduction process. Okay, then so the surface concentration of oxidized species would decrease from the 1 millimolarity to 0.5 millimolarity. Then let me go forward to the negative direction. Then finally we reached the peak current point. Here is the point D. And at the point D, we have this kind of concentration profiles for the oxidized species Fe3 plus and the reduced species Fe2 plus. The most interesting point is that the surface concentration of oxidized species is going to 0. Let's go back to the point C. At this point, we have 0.5 millimolarity of Fe3 plus. But at the peak point, the all molecules of Fe3 plus is totally converted to Fe2 plus. So you cannot find any molecules about Fe3 plus on the surface of electrode. At the same time, the concentration of Fe2 plus is maximized. Maybe the surface concentration of Fe2 plus is about 1 millimolarity because all of the surface oxidized species is going totally to the reduced species. So let me check the concentration gradient of the point D. I mean of oxidized species Fe3 plus. Then the slope is increasing from this slope and this slope. So the current is maximized for the reduction process. This value is about 21 microampere here. Then let me say again, the surface concentration of oxidized species is 0. Then let me move the point from D to E, more negative potential. What happens? You cannot move or you cannot decrease the surface concentration of oxidized species to the more negative value because negative concentration does not exist actually the negative concentration of oxidized species is out of sense. So still we have zero concentration of Fe3 plus here, but the diffusion layer, let me say this length of the yellow area is called diffusion length. So diffusion length decrease, the diffusion length increases from C point and then D point and then E point. Why? Because more amount of oxidized species is reduced because you have applied more negative potential. However, you cannot change the surface concentration of the oxidized species. So, as the diffusion length increases, then the slope of the concentration gradient of the oxidized species decreases from the D point to E point. Then the corresponding current would decrease. So right now, at the maximum point, I have said 21 microampere. Then right now, at the E point, we have 13 microampere there. So current decreased from D point to E point. And then at the F point, I have inversed the potential sweep from negative potential to the positive potential. Now let's go to the G. We are still on the cathodic process because the current is cathodic. Then what happens? At the point G, still we have the concentration, surface concentration of oxidized species at 0 millimolarity. However, the thickness of diffusion layer increases. So the slope of the concentration gradient decreases, then you would obtain the 6 microampere, which is less than the 13 microampere. So right now we are at G. Then let's go to the anodic process. I'm moving from G to I point. Then at the I point, the surface concentration of oxidized species increases again back. So let me check the previous point G. We are on the 0 surface concentration of oxidized species. Right now, the 0 concentration is going back up to some the concentration of oxidized species. Let me say 0.5 millimolarity. At this point, 0.5 millimolarity oxidized species or Fe3 plus. So right now you have this kind of profile for the Fe3 plus or oxidized species. Then the concentration gradient direction have changed from this direction indicates plus, then this direction indicating negative direction. So right now you should have the negative current or anodic current, oxidation current. So let me say this slope indicates minus 6 microampere here, minus 6 microampere. Then right now you have the gone forward to the more positive potential. Then finally the surface concentration of oxidized species is going back to 1 millimolarity. This was the original concentration of the oxidized species. So let me say this point is 1 milli. Sorry, this is not voltage, molarity, and millimolarity F is 3 plus. Then the slope of the concentration gradient, actually negative concentration gradient, was increasing from here to there. So more negative oxidation current flows from this system. Then we are going from the point J at which the maximum anodic current is obtained to the point K, because we are sweeping the potential from the negative potential to the positive potential. Then the more oxidized species is generated, and then total amount of the oxidized species increase from here to there. So the concentration at the middle point of the diffusion layer is increasing from this one to this one. Therefore, the slope would decrease from the point of negative direction. Then the current changes from minus 16 microampere to minus 4 microampere. Then finally we go back to the K point. Even at the same position from the viewpoint of the potential to the initial point, we cannot have obtained the initial concentration gradient, like only 1 millimolarity of Fe3 plus and only 0 millimolarity of Fe2 plus. Even at the same potential, we have some portion of Fe2 plus there, and then we have some concentration less than 1 millimolarity at the middle point of the diffusion layer. So at the last point of the cyclic voltammogram, we have on the anodic process, we have obtained some value of anodic current. Then when you are going back to the fold scan, you have a new starting point from here. Then you will follow this line, and then finally follow the same point of the fold scan. I have explained that. So you should understand the cyclic voltammogram from the viewpoint of concentration gradient. You have learned about the Landry-Sevcik equation and the reversible electrochemistry in a diffusion limited system should follow the Landry-Sevcik equation. However, sometimes you can meet the deviation from Landry-Sevcik equation in terms of scan rate dependency. Let me check that kind of possible deviation for even for the reversible reactions. Here is the plot for the peak current versus scan rate, and then this line indicates the Landry-Sevcik line, at which the slope is the 0.5 or 1/2. That is the Landry-Sevcik relationship between the peak current and scan rate in the log scale. So you can easily find that the scan rate dependency follows the Landry-Sevcik line faithfully at a relatively slower scan rate, in this case less than 100 millivolts per second. So you can find the several points on the lines of RS line, Landry-Sevcik line, up to 100 millivolts per second. However, surprisingly or strangely, at a relatively faster scan rate, the peak current deviates from the Landry-Sevcik line here. So there is some deviation. Usually you have had the smaller peak current than less than the expected value by Landry-Sevcik equation. So why you should have the deviation at higher scan rate? Here is the reason. At too fast scan rate, potential goes forward to the direction of scan. before the current is fully developed. If your scan rate is much slower than the kinetics of mass transfer or kinetics of diffusion, then you should obtain this kind of ideal cyclic voltammogram governed by Landry-Sevcik equation. The peak point should be placed on the line of RS line or Landry-Sevcik line. However, because potential goes forward to the direction of scan before the current is fully developed, so the dark head of cyclic voltammogram is broadened like that, with corresponding peak current decreasing. So the current peak decreases from the ideal case to the real case like that, because the dark head of cyclic voltammogram is broadened. The peak area should be the same as the peak area of ideal cyclic voltammogram, because total amount of the reduction in this case of oxidized species should be the same for the ideal case and the practical case. However, the dark head is broadened by the too fast scan rate, then the peak current is measured less than the value expected from the Landry-Sevcik equation. So you should have this kind of deviation from the RS line. Therefore, I can say reversibility is a relative concept which should be compared with scan rate. Let me think about another strange and interesting scan rate dependency. Here is the situation. You have an electrode and oxidized species here, let me say ox. And ox can be reduced into the red one, that is the reduced species, by getting the electron from the electrode. So this is the electrochemical process, or let me say this is the E step. E step. However, in this special case, we have one more thing. M-red1 is chemically converted to M-red2, red2, without the effect of the electrochemistry. So this is called chemical step or C step. This is the C step. This red2 cannot be electrochemically oxidized into ox. However, this red one is electrochemically oxidized into ox. And also, this charge transfer reaction is reversible. Then, what happens for the scan rate dependency about this case? To investigate the scan rate dependency of this reaction in the presence of C step, I have obtained several cyclic voltammograms at various scan rate. The smallest one is about the cyclic voltammogram obtained at 50 millivolt per second. The next one is 100 millivolt per second. The third one 250 millivolt per second. And the last one 500 or 1000, 2000, even they are not given to you here. Then I have picked up the peak points from the cathodic process, cathodic process and anodic process. Then I have plotted those experimental data in this plot, like y-axis is the peak current and x-axis is the scan rate in log scale. Then let me think about the scan rate dependency about the cathodic process. Cathodic process means ox is going to red 1 here. In this case, we have obtained very practical the relationship between the peak current and scan rate. It means at slower scan rate, relatively slower scan rate, my experimental data is following the Landry-Sevcik relationship faithfully. However, higher than 1000 millivolts per second, there is a tiny deviation from the Landry-Sevcik line because the potential is going forward to the scan direction before the current is fully and totally developed. So I have said about that in the previous slide. So there are no weird thing found in the cathodic process. And then let me go to the anodic process. In this case, anodic process means the oxidation, electrochemical oxidation of red 1 to the ox or oxidized species. So around 1000 millivolts per second, the experimental data is following faithfully the Landry-Sevcik equation. At higher scan rate, there is some deviation which is expected from the too fast scan rate to to overcome the mass transfer kinetics. So we could expect it. However, even at slower scan rate, we have another deviation. So why? Why should we have this kind of the negative deviation from the Landry-Sevcik equation even at slower scan rates? The main reason is the C-step from mRad1 to mRad2. Let me think about that. So if you are scan the potential at this range around 1000 millivolts per second, then mRad1 is going to mox. However, there is no time for the mRad1 to be converted to mRad2 because we are using the scan rate fast enough to not to give the time to the chemical step. So most of mRad1 is converted to mox. So let me say about the molarity. After the reduction of oxidized species, let me say 1 millimolarity of oxidized species, then which is converted to 1 millimolarity red 1. At relatively higher scan rate or faster scan rate, which is faster than the chemical change for the C-step, all of the 1 millimolarity is devoted to the oxidation, electrochemical oxidation to the oxidized species. So the anodic peak current is estimated at the value expected from Landry-Sevcik equation. I mean, the C-step cannot affect the electrochemical oxidation of red 1 to ox. And then let me slow down the scan rate. So red 1 is slowly converted to the oxidized species. It means we have enough time for the C-step or chemical reaction or chemical conversion from red 1 to red 2. Then what happens? So in this case, only a portion of mRad1 is going to the oxidized species. Let me say 0.5 millimolarity of red 1 is going to red 2. Therefore, we have only 0.5 millimolarity of red 1. So, only 0.5 millimolarity red 1 is electrochemically converted to oxidized species. The smaller amount of reactant indicates smaller current. So, you should have obtained the deviation, negative deviation, from the Landry-Sevchin line to the smaller values of anodic process. So it is the reason why we should have obtained the negative deviation from the Landry-Sevchin equation even at the very slow scan rate. So the chemical reaction affects the electrochemistry in this situation. Again, if the scan rate is slower than the kinetics of chemical change for the C step, then the peak current of anodic process becomes smaller than the value expected by Landry-Sevchin equation. So you should think about the deviation of reversibility when you have included the presence of chemical step. You have just finished voltammetry sections. The voltammetry includes linear sweep voltammetry and cyclic voltammetry for non-Faraday processes and also Faraday reactions. This is the second electroanalytical method, which is the Chrono and Perimetry. Chrono means time and amperometry means current. So the resultant plot is based on current versus time. Let me start with non-Faraday process for the Chrono and Perimetry. The input stimulus is constant potential you have applied. So y-axis is the potential and x-axis is the time. So you will apply a constant potential or voltage into the system along time. Then let me expect what kind of current versus time curves are obtained. Here, there is the resultant plot. Y-axis is the current and x-axis is the time. And let me define two parameters for a schematic explanation about the current decrease of the Chrono and Perimetry. So n infinity is the number of extra charges developed by an applied potential. Let me say I have applied a potential. Then 3 extra negative charges are developed on the electrode. In this case, n infinity is 3. This number can be interpreted as the maximum number of ions that is allowed to accumulate on electrode surface. So, to compensate the extra negative charges by applied potential, we need to have 3 cations on the surface of electrode. That is the n infinity. And the next parameter is n. N is defined as the number of available ions to move toward the electrode. Then let's start with some applied potential. So right now, again, we have 3 minus charges in the electrode. And then just after this potential with 3 negative charges applied into the system, then three cations are starting to move toward the electrode. So at the point A, we have 3 for the number of available ions to move toward the electrode. 3 cations are moving. So the 100% of cations relative to the maximum number of ions that is allowed to accumulate on electrode surface is moving. So we could have a maximum current is obtained. Then let's go to the point B. I mean about 10 microsecond just after the applied potential. So what happens? One of 3 available ions finally reached the surface of electrode. Then one of the extra negative charges of electrode was compensated by this cation. However, still we have moving 2 cations, which is moving toward the electrode. So the available ions for charge movement per the n infinity is about 67%. Then from 100% to 67%, the current decreased here, from here to there. Then let's go to the point C. Right now, we have 2 cations sitting on the surface of electrode, and then only 1 moving cations are available. So 33% of the maximum number of ions that is allowed to accumulate on electrode surface is moving. So 33% of the initial current would be obtained. So another current decrease from point B and point C. Then current is continuously decreasing to some point. At this point, right now, we have all of the available cations for movement are sitting on the surface of electrode. So 0% for the available ions per the maximum ions. Then at point D, we cannot have any more current. So our expected picture about the current versus time is the maximum current just after the applied potential, then current is decreasing along time, and then finally it is going to the zero current. That is the current versus time curve for the non-Faraday processes of Chrono and Perimetry. Let me try to get the governing equation for the Chrono and Perimetry. I have said non-Faraday processes are split into 2 different processes. The first one is charge movement toward the electrode, and then the second one is charge accumulation on the surface of electrode. Then the overall potential is split into 2 potential difference. The overall potential is fixed at constant value because this is the Chrono and Perimetry. The first one is about the resistance. So the potential can be converted to the product of current by solution resistance. Plus the second potential term is Q over capacitance, double layer capacitance. Then after taking a derivative, we could obtain 0 because d dt, the potential is constant, so d dt is going to 0, and then rs, which is not the function of time, and di dt plus 1 over CD. Here AA capacitance is not the function of time, so dq dt. Then dq dt is going to current, then which is equal to 0. This is very simple ODE, ordinary differential equation, because we don't have any constant term here. So let me get together the current function. Di per I is equal to minus time constant, 1 over time constant dt. And here is the initial condition. So at time equal to 0, of course, we could assume that the accumulated charge is 0. Then let me put this condition into here. So Q is going to 0. Then you can remove this last term. Then current is equal to the constant potential per resistance. So current is equal to applied potential per solution resistance. Then with this initial condition and this governing equation, you could find the solution like that. Current is equal to the initial current with exponential function of minus t over tau, time constant. You have the same parameter. You have the same parameter for the voltammetric situations also. So this is the function. From the previous slide, we have expected that the maximum current would be obtained, then the current decreases along time, finally going to 0. This behavior is described by this exponential decrease function. The first point is the initial current, which is defined by the constant potential you have applied divided by solution resistance, and then following the exponential decay of current along time. Let me think about the time constant. I have said the time constant tau as a measure of the speed of response of your electrochemical system. So as time constant increases following this arrow, the non-Faraday process ends longer. So at extremely fast, at the extremely the small time constant, like time constant equal to 0, you would obtain this function. The initial current is just going down abruptly and then going to 0. That is the most extreme case of the smallest time constant. However, as time constant goes up, then you would have some time before reaching current 0. So then here on this curve, you can find you need to have very long time before reaching the 0 current. So anyway, in any cases, if you have enough time, your system is going to 0 current, and the time constant will define the response time of your system. That is the Chrono and Perimetry for non-Faraday processes. And then it's time to go for the Faraday reactions. Here is an reversible Faraday reactions in a diffusion limited system. So in the same way, you have applied the constant potential into the system at time equal to 0. Then the result would follow a similar behavior shown in the non-Faraday process. Again, At time equal to 0, we have a very large current, and then the current decays a long time like that. So why can we expect this kind of current time function for the Faraday processes or for Chrono and Perimetry? Actually, almost similar situations would explain these current time curves. Again, here is the current time curve for the reversible Faraday reactions in a diffusion limited system. We should think about the equilibrium situations. I mean, we have applied a fixed potential, and at this applied potential, we should have an equilibrium constant, or the ratio of reduced species per oxidized species at equilibrium. So let me assume that I have applied minus 300 millivolt. This is just a schematic assumption. I have just applied minus 0.3 volt, which is applied to the system, and then at this potential, we should have the same amount of reduced species and oxidized species. So it means the equilibrium constant at this applied potential is equal to 1. So we should obtain this value in terms of equilibrium constant at after a long time experiment. And also let me define n infinity and n parameter n again for the Faraday reaction. In these Faraday reaction situations, n infinity is the maximum number of oxidized species that is allowed to be reduced on electrode surface. So, for example, if you have 6 molecules of oxidized species, then the maximum number of oxidized species which is going to approach the equilibrium constant is 3. So if after 3 of them is reduced into the reduced species or red solid ball, then like that 1 2 3, then we would obtain the equilibrium constant at 1. So, and in this case, n infinity is equal to 3. And what is the parameter n? N is the number of available ions to be reduced. So at time equal to 0, we have an electrode and you have applied minus 300 millivolt to the electrode, and then let me assume that 6 oxidized species are available on the surface of electrode. And what we know is that 3 of them will be reduced finally. Therefore, n infinity is 3, because that is our destiny in terms of thermodynamics. And then all of 3s are available as the oxidized species, which will be reduced. So 100% opportunities to provide a Faraday current. That is the situation on the point A, just after you have applied minus 300 millivolt to electrode. And then let me say 10 microsecond or 100 microsecond later, one of the 6 oxidized species is reduced into the reduced species, the solid red ball. Then the available the number of available ions to be reduced is 2 per the maximum number for the oxidized species which is allowed to be reduced on electrode surface is 3. So 67% will provide the current. So the current would decrease. And then one more oxidized species is reduced. Then 33% can be oxidized, can be reduced. So current is going down. And then when the time approaches infinity, finally we have 3 reduced species, which can be considered as the equilibrium situation. So there are no more driving force, then the current is going to zero. The situation of these Faraday processes in a diffusion limited system is very similar to the non-Faraday process for Chrono and Perimetry. So at time equal to 0, we could have a maximum current, and the current would decay along time, finally approaching 0. So they are very similar, independent of Faraday reactions or non-Faraday processes. Let me introduce the equation to describe the current decay of Chrono and Perimetry. We are still thinking about reversible Faraday reactions in a diffusion limited system. That is to say, the kinetics is determined by diffusion equation. The Cottrell equation is the equation to describe the current decay. Let me check the Cottrell equation. Current is proportional to NFA. N is the number of electron transferred, Faraday constant, and the area of electrode you have used for experimental data, diffusivity, root square of diffusivity, bulk concentration over the root square of the product of pi and time. That is the Cottrell equation. The most important point of the Cottrell equation is that current is inversely proportional to the root square of time. That is to say, the product of current and the root square of time should be constant. This constant is called Cottrell equation. Also, from the Cottrell equation, you could calculate the diffusivity. Let me check the Cottrell equation again. Here is the current. This is the experimental data. How about time? Also experimental data. And the number of electrons transferred is usually known from the electrochemical reaction equation. Faraday constant, area of electrode, you should know about that, and bulk concentration, you have made it. So diffusivity could be calculated from the Cottrell constant. So you can obtain the diffusivity. Let me compare the current decay function between the Faraday reactions and non-Faraday processes. For the Faraday reactions, again, current is inversely proportional to the root square of time. However, for non-Faraday processes, current is proportional to the exponential function of time. That is the different point. However, there are common things. In both cases, the current decreases and then approaching to the zero values of current. However, the detailed function of time is different between reversible Faraday reactions and non-Faraday processes. That is the Chrono and Perimetry. You have learned about two categories of electroanalytical method. The first one was the voltammetry, including linear sweep voltammetry and cyclic voltammetry. The second category of electroanalytical method was chrono and perimetry, at which we have applied a constant potential into the system. And then here is the third category of the electroanalytical method, which is the Chrono Potentiometry. In this case, we will apply a constant current instead of a constant potential. Before going to the body of Chrono Potentiometry, I'd like to think about what the meaning of applying constant current versus applying constant potential is. So I'd like to emphasize the difference between the constant current method and the constant potential method. I'd like to feed my puppy or my baby. Then I believe there are two different methods available. The first method is feeding my puppy with a fixed amount, which is about the constant potential method. So here I have fixed the amount of food in a bowl. So I have poured a pouch of doggy food into the bowl. And then I will let my doggy eat all of them. Then at the same time, I'd like to measure the eating rate, I mean food per second, a long time. At the very first time, my puppy would eat at a very fast value of eating rate. However, after getting some food, then the eating rate would be slowed down. When the bowl is empty, almost empty, then the eating rate is approaching to zero because my doggy is full of food. That is like constant potential method, and the constant potential means fixing the amount of the food. Let's go to the second method to feed my baby. Here, I'm feeding my baby at a fixed feeding rate, like 1 spoon per minute. And then I will measure the belly size of my baby. At the very first time, the stomach of my baby was shrunk because he is very hungry. When the food is introduced into the empty space of the stomach, the size of the stomach is rapidly increasing, and then to be the normal size of the stomach. Still, I'm feeding my baby at the same feeding rate, like 1 spoon per minute, and then the empty space is filled out by the food from here to there, and the volume change is not very significant, unlike at the very first time. However, the volume of stomach would increase slowly. After the stomach is full of food, then probably my baby would resist to eating. So the belly size of my baby is a function of time following this kind of curve. That is the constant current method. In this constant current method, I have controlled the feeding rate. Actually, I have fixed the feeding rate for my baby. Then I have checked the belly size or potential a long time. Those are the difference between the constant potential method and constant current method. Again, the constant potential method is like feeding my puppy with a fixed amount of food. However, the constant current method is like feeding my baby with a fixed feeding rate of food. Let's go to the body of Chrono Potentiometry. Of course, the first case is about non-Faraday process. The input stimulus is the constant current, like that, a long time. And then what happens for the potential? As you know, the non-Faraday process can be considered to be split into two processes. The first one is charge movement, and the second one is charge accumulation. When you apply the constant current into the system, the system feels the resistance at the very first time. So here is the ohmic the drop of the potential. The size of the potential drop or increase is measured by Ohm's law. V is equal to IR, solution resistance. Then we have fed one electron first, and then one cation is approaching to the surface and then finally sitting on the surface of the electrode to compensate the extra negative electron which is developed on the electrode. And then one more electron is introduced into the electrode, and at the same time one more cations is sitting on the surface of electrode, and then third one. So we could expect the potential function is linear in terms of the time. Let me derive the equation. We are using the same equivalent circuit which is used for non-Faraday processes for cyclic voltammogram or linear sweep voltammogram or Chrono and Perimetry. The overall potential is equal to Ohm's law plus Q over capacitance, which is about the charge accumulation. Q is the product of current and the time. So the final equation like that. And then in this equation, current is the constant value. So potential would increase with time. The slope is I per capacitance. I per capacitance. Of course, again, this current amount is fixed at a constant. And the y-intercept is I by solution resistance. That is the non-Faraday process for Chrono Potentiometry. Okay, then let's go to the Faraday Gradient case. Here is a reversible Faraday Gradient in a diffusion limited system. Of course, the input stimulus of Chrono Potentiometry is the constant current. Then let me assume that I have applied plus 1 milliampere per centimeter square, which indicates the cathodic current. I mean, by using this current, we will induce the reduction process. It means we could expect that the potential would shift to the negative direction. Then what happens for the potential time curve? Let me say this: we are investigating the electrochemistry of the reduction of Fe3 plus to Fe2 plus, or empty ball to the filled ball, filled red ball. The potential is determined by the composition of the oxidized species and reduced species, or this is for the Fe3 plus and this is for the Fe2 plus. So potential is equal to standard reduction potential minus RT and F log composition ratio, product per reactant. And then here is the schematic situation on the surface of electrode. At the very first time, what we have on the surface of electrode is only oxidized species, or Fe3 plus, because I have introduced only Fe3 plus without Fe2 plus. Then let me assume that we have 1, 2, 3, 4, 5, 6. 6 the empty balls are there. I mean 6 oxidized species are there. Each balls represent, for example, 10,000 molecules of oxidized species. Anyway, let me calculate the potential by using this equation, or Nernst equation. So at the very first time, what we have is only oxidized species. So 0 per 6, or 6 groups of oxidized species. And then this is 0, and log 0 is going to the minus infinity, and this term is going to plus infinity. So we obtained the plus infinity potential for this case. Plus infinity potential indicates we have a very big tendency to be reduced. So even without any applied potential, some portion of oxidized species is converted to reduced species. So let me say that 1 of 10,000 molecules of oxidized species is reduced into the solid ball, or reduced species. So I have some partially filled ball here. It means the 1 of 10,000 oxidized species is converted to the reduced species. In this case, the reduction potential is going to around 1.0 volt. Before we have applied the constant current. Then this is the starting point, which is on the 1.0 volt. It's time to apply a constant current into the system. Just after I have applied a constant current into the system, the curve would follow the non-Faraday process. At the very first time, the ohmic drop happens, the amount of which is I by solution resistance, like that. And then going down linearly with time. Then right now we are around point A, well, before the point A. Then we have reached some potentials at which some portion of oxidized species is reduced into the reduced species. Then let me say, At point A, one of 6 empty ball is reduced into the solid ball. Then the value of solid ball is right now 1 and the empty ball is 5. So the calculated value of the potential is about 0.81 volt. So the potential decreases to 0.81 volt. I'm using constant current. So after the first reduction, then we are getting the second reduction. Right now, at this situation of point B, we have 2 solid ball and 4 empty ball. The calculated value of the potential is estimated at 0.79 volt, so going down. And then one more reduction, 0.77 volt, one more reduction, 0.75 volt, and one more reduction, 0.73 volt. Or finally, the most of molecules on the surface of electrode is reduced. Then the potential is fastly going down. So like that. And let me check the C point. In this situation, we have the same amount of empty ball and the solid ball. It means standard state. Let me check it. 3 solid balls and 3 empty balls. So log term is going to 0. So the potential is equal to the standard reduction potential. So the potential of C point would be plus 0.77 volt because the standard reduction potential of electroactive species pair of Fe3 plus Fe2 plus is plus 0.77 volt. So this kind of graph is obtained as the result of the Chrono Potentiometry. Again, at the very first time, non-Faraday process, ohmic drop, and then linear decay of the potential, and then the decay ratio is going down, and then relatively plateau. Then after the most of oxidized species is reduced, the potential is rapidly going down. This is the whole picture of the Chrono Potentiometry. Could you remember the Carter equation for Chrono and Perimetry? The Carter equation is the equation to describe the Chrono and Perimetry. Here is the Sandy equation for the Chrono Potentiometry. Actually, this Sandy equation is obtained from the reversible Faraday reaction in diffusion limited systems, like in the Carter equation. The Sandy equation and Carter equation is very similar to each other. So let me think about that. In the Carter equation, you can find the current is inversely proportional to the root square of time. In the Sandy equation, current is inversely root square of tau. Tau is a kind of time, but it is not just time. So let me introduce the concept of tau in the following figure. But right now, I'd like to compare the other terms. Also, NFA is here, and root square of diffusivity, and root square of diffusivity, and bulk concentration, and the same. So Carter and Sand are very similar to each other. So the most important part is, of course, in the Sand equation is current is inversely proportional to the root square of tau. Then let me think about what uh, the tau means in the Sandy equation. Here is the Chrono Potentiometry curve. Y-axis is the potential, and x-axis is time. And then you can follow these curves for the response of Chrono Potentiometry. At the very first time, the current decreases rapidly, and then following some slightly inclined plateau there, and then at the end of the reaction, the potential is decaying in a very fast way. So you can find the slightly inclined plateau for this chrono potentiometry curve. This slightly inclined plateau indicates Faraday reactions. How about those two lines, rapid decay of potential? It indicates, they are closer to the vertical line, and it indicates non-Faraday process. Between two non-Faraday processes, you can find the Faraday reaction. The value of tau is a measure of plateau length, like in this picture from here to there, and also indicates the amount of electrochemical reaction or the amount of electroactive species. Let me say that we have 100 molecules of oxidized species. So let me say 100 Fe3 plus. Then in this case, for example, tau is measured at 100 seconds. Then I'd like to reduce the amount of Fe3 plus in the electrolyte from 100 to 10 Fe3 plus. What is the value of tau in this case? Of course, tau is 10 seconds. So again, tau is a measure of the amount of electrochemical reaction or the amount of electroactive species, in this case Fe3 plus, or the electrochemistry between Fe3 plus and Fe2 plus. Okay, then let me think. So let me go back to the Sandy equation. Here is current, and here is the root square of tau, and then the product of current and root square of tau must be constant in the Sandy equation, because NFA is constant and diffusibility constant, bulk concentration is constant if you have fixed electrolyte for your system. So if this value, the product of current and the root square of tau is constant, it means your system has the reversible Faraday reaction. Also, your system is limited by diffusion. Let me think about the deviation from Sandy equation. What kind of situations induce the deviation from Sandy equation? Here is the Sand constant versus current plot. This is the product of current and the root square of tau, and x-axis is the current. So if you have an ideal situation where you have reversible Faraday reaction in diffusion limited systems, you should have the constant value about the sand constant independent of current. If you have obtained this kind of plot, it means your system is following the reversible Faraday reactions in diffusion limited system. Let me split those curves, those regions, into two different regions. The yellow space indicates low current region, and green one is about high current region. In the low current region, current is slower than diffusion rate. So the overall kinetics is limited by current, or the overall kinetics is limited by electron feeding or extracting rate. So again, in this region, current would limit the overall kinetics. So it's not important thing what kind of process is used for the system, because the applied current would limit the overall kinetics in this low current region. Then let me go to the high current region. So you have increased the current which is applied to the system. And then right now, diffusion process is slower than the current. So diffusion rate limits the overall kinetics. In that case, you have the constant. So let me think about other cases which is not limited by diffusion. The first case is adsorption case. Here, oxidized species is strongly bound or adsorbed on the surface of electrode. And then at high current region, we don't need to think about the diffusion. So we would get the higher current than the diffusion controlled system. So in this case, or the adsorption case, strong adsorption case, would show the positive deviation from the Sand equation. Let me go to the second case, and then we are investigating the electrochemistry for any cases, like ox is going to red, oxidized species and reduced species. In this second cases, we have one more step. That is the chemical step. So ox star is chemically converted to ox, and then ox is converted to the reduced species. The current applied to the system controls the electrochemistry, not the chemical step. So at low current region, the electrochemical step, or E step, is slower than the C step. Let me write down E and C here. So ox to red is E step, and ox star is going to ox is C step. So at low current region, E step is slower than C step. So current would limit or determine the overall kinetics. So it will follow the Sand equation. However, at high current region, C step is slower than E step. So the overall kinetics is limited by C step. Ox star is going to ox. So we would have the negative deviation from the Sand equation. In the subchapter 2, I have introduced three categories of electroanalytical method. The first one is voltammetry, the second one is chrono and perimetry, and the third one is chrono potentiometry. Then in this subchapter 3, I'd like to say about the components of electrochemical cells, plus some technical tips for the electrochemical experiment. Here is the electrochemical cells. Of course, we need to have 3 electrodes for electroanalysis. The first one is working electrode, and you will investigate some electrochemistry on the surface of working electrode. The second one is reference electrode, which provides a constant potential into the system. We are measuring the potential difference between working and reference electrode. And the other thing is counter electrode. The current flows between working and counter electrodes. Here is the popularly used working electrode, and those 3 electrodes are the disc electrodes. The first one is made of glass carbon, and the next one is the gold, and this one is the platinum. And here is the cross-sectional view of the disc electrode. At the tip of the electrode, we have gold or glass carbon or platinum disc. And this disc electrode is connected to the electrically conductive rod. Of course, the rod and the disc is wrapped with the body of electrode, like Teflon or some inert plastic. That is the working electrode. And the second one is reference electrode is here. As you know, we are using an electrochemistry inside of reference electrode to provide a constant reduction potential. In this case, this is the silver chloride reference electrode, and here is the silver wire. On the surface of silver wire, we have the silver chloride solid. And then also we should have some electrolyte, which is the saturated KCl solution. At the tip of the reference electrode, we have a porous junction. And through this membrane, some ions are introduced into the reference electrode or vice versa. The third one is counter electrode. The surface area of counter electrode should be larger than the working electrode. So sometimes we are using a coil type counter electrode, which is the platinum, and the other thing is platinum gauze electrode. So we need to have those 3 electrodes, working, reference, and counter electrodes for electrochemical cells. Before analyzing your samples, working electrode and reference electrode should be checked. Are they really working properly? Obtain cyclic voltammograms for a well-known electrochemical system. Then you can check the conditions of working electrode and the reference electrode. Here is an example. I'd like to use 100 micromolarity potassium ferricyanide in 50 millimolarity phosphate buffer solution at pH 7. The first one is the electroactive species, and the second one is the supporting electrolyte to suppress the migration effect for the overall electrochemistry. We are using this electrochemistry. Then ferricyanide based on Fe3+ is reduced into the ferrocyanide based on Fe2+. The reduction potential of this electroactive species is about 240 millivolt versus silver chloride. To obtain the cyclic voltammogram of this electroactive species, I have used 100 millivolt per second as the scan rate of cyclic voltammogram. Then, how to check the surface condition of working electrodes? I have used three different electrodes: the electrode A and electrode F and electrode E. The electrode A shows very handsome duck-shaped cyclic voltammogram. Probably this electrode A has the practically best condition. Let me check the peak-to-peak gap. Ideally, the peak-to-peak gap should be 60 millivolt for single electron electrochemical reaction. Let me check the peak potential. For the cathodic peak potential is 200 millivolt is measured, and 280 millivolt, which is the anodic peak potential. So peak to peak gap is 80 millivolt. Practically, the peak to peak gap less than 80 millivolt is acceptable. So I could say the electrode A is not bad. Let's go to the second electrode F, dashed line. And the peak-to-peak gap is measured at 400 millivolt from here to here. So I could say the electrode F has the poor surface condition to hinder electron transfer. This value is much larger than the ideal value at 60 millivolt. So, surface of working electrode should be cleaned by mechanical and or electrochemical polishing. Let's go to the third one, dot lines. Electrode E. This shows extremely poor surface condition in terms of electron transfer. You can find the cathodic peak potential, cathodic peak. However, I cannot find the anodic peak here. Maybe if you extend the potential to the more positive value, you could find some anodic peak. So the peak-to-peak potential would be about 1500 millivolt. So this big peak-to-peak gap indicates extremely poor surface. Then, how to polish working electrode? We have two different methods about polishing. The first one is mechanical polishing, and the second one is electrochemical polishing. Let me start with mechanical polishing. Wet polishing pad, here is the polishing pad, before adding polish. So just pour some drops of water onto the polishing pad. Then add a small amount of polish powder to the wet pad. We could use several powders in terms of size, and usually at the very first time 1 micrometer size alpha alumina is the best. After polishing the surface of electrode with this bigger size alumina, then we should go to 0.05 micrometer gamma alumina. You could purchase the commercial product of alumina powder from Buehler, the company name. Okay, so right now you have the polishing powder on the polishing pad, and then this is the electrode. Use smooth motion like infinity and even pressure when polishing. So polish your electrode by using this kind of motion, like 100 or 1000 times polishing is required to clean the surface of your electrode. Let's go to the second method, which is the electrochemical polishing. And this electrochemical polishing is not necessarily required, and then you can skip this step. Scan electrodes in 1.0 molarity sulfuric acid 10 times from -1 volt to +1 volt at 100 millivolt per second. That's it. By using the electrochemical polishing, you can form the surface functional groups on the surface of electrode, and then hydrophilicity of your electrode is improved. As a result, charge transfer kinetics is improved. Then let's go to the reference electrode. So as the first step, obtain reference reduction potential from a benchmark reference electrode. So a benchmark reference electrode means good reference electrode. Then calculate the average value of the peak potential. So cathode peak potential plus anodic peak potential per 2 is the average potential of the benchmark reference electrode. Let me say this cyclic voltammogram is obtained from your benchmark reference electrode. Then the average peak potential is measured at 240 millivolt versus silver chloride for ferricyanide electrochemistry. This value will be used as the reference, and then measure the average peak potential of your reference electrode. Deviation of average potential of your reference electrode from the ideal value of the benchmark reference electrode indicates the potential shift of reference electrode. If the difference between your electrode and benchmark electrode is less than 40 millivolt, and then you can say, my electrode is not bad, so you could use the reference electrode for your experiment. However, if the difference is larger than 40 millivolt, then you should fix your reference electrode. Fill out the test reference electrode with new electrolyte. So in this case, you have the silver chloride reference electrode, and open the head of the reference electrode, and then take the old electrolyte from the reference electrode, and then introduce the new freshy reference electrolyte into the reference electrode. Or change the membrane. Here is the membrane. Or if you have failed to fix your reference electrode by using those two changes, then you should use new reference electrode. Or you can use temporarily the problematic reference electrode by just adjusting the reference potential. Here is alternative method to check whether reference electrode works properly. This is your test electrode, and the other thing is benchmark electrode. And then please measure the potential difference between those two electrodes by using the voltmeter. Again, if the difference is larger than 40 millivolt, then you should fix your reference electrode or change the reference electrode. You could find various reference electrode like normal hydrogen electrode or standard calomel electrode. One of the most popular reference electrode is silver chloride, and also you can make this silver chloride reference electrode in your lab without large cost. Actually, the commercial product of silver chloride reference electrode is very expensive. Step 1, you have a capillary tube, and you have a short platinum wire, and then hit the end of capillary with a short platinum wire here, and the end of the capillary shrinks to hold the platinum wire. Around the platinum wire you have some channels for ions to silver chloride reference electrode. Anyway, you have made the body of the reference electrode, and then it's time to make the electroactive electrode. Here is the silver wire, and then polish the silver wire by sandpaper and then heating. Then put the silver wire into the hydrochloric acid. You can make the hydrochloric acid solution by introducing 2 to 3 drops of hydrochloric acid, concentrated hydrochloric acid, into 100 milliliter water. Then apply a constant potential at 0.75 volt versus silver chloride, and then obtain the cyclic voltammograms. No. This is the Chrono and Perimetry, and you have applied a constant potential into the system at 0.75 volt for 300 seconds, and the shiny surface of silver wire is turned light gray color. It means you have made some silver chloride coating on the silver wire. So you have electroactive electrode here. This is the Chrono and Perimetry obtained from the plating the silver chloride on the surface of silver wire. So at the very first time you have a maximum value of current, and then going down for 300 seconds. So right now you have two things: the reference electrode body and the electroactive electrode. Let's go to the third step. By using tube, you can introduce some electrolyte into the capillary tube with platinum wire. The electrolyte is the saturated potassium chloride prepared by introducing about 35 grams of KCl into 100 milliliter of water. Then insert silver chloride coated silver wire into the capillary, including or having the electrolyte. Finally, wrap the open end with parafilm or Teflon tape. That is the silver chloride reference electrode. Okay, additional information. Technical tips related to electrodes. This is the list of representative reference electrode. NHE for normal hydrogen electrode. The reduction potential of normal hydrogen electrode should be 0 millivolt versus NHE. SC stands for saturated calomel electrode, while the other thing is sodium saturated calomel electrode, SSC, have 242 or 236 millivolt as their reduction potential. There are two types of silver chloride electrode, and the first one have one molarity KCl as electrolyte. The second one have the electrolyte, which is the saturated KCl. So the reduction potential of those things are 222 or 197 millivolt respectively. The other thing is mercury sulfate reference electrode or copper sulfate reference electrode. The other box is devoted to the working electrode potential ranges in aqueous electrolyte. The most popular disc electrode having glass carbon, gold, and platinum, and they can be used for the +1 to -1 potential range. Here, 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 around there. And then the other thing, mercury electrode. And mercury electrode is more specified to more negative the potential window. So mercury can be used from 0 to -2 volt of the potential.